Today we're going to explore one of the most fascinating phenomena in physics, Leidenfrost Micro Hovercrafts. These are tiny droplets that not only levitate on hot surfaces, but can actually race uphill on their own. First, let's understand the basic Leidenfrost effect. When you place a liquid droplet on a surface that's much hotter than the liquid's boiling point, something remarkable happens. Instead of boiling violently, the droplet levitates on its own cushion of vapor. This vapor layer insulates the droplet from direct contact with the hot surface, allowing it to survive much longer than you'd expect. The key insight is that the droplet never actually touches the hot surface. There's always a thin layer of vapor between them, typically only about 100 micrometers thick. Think of it like a self-generating air hockey table. The heat from the surface continuously evaporates the bottom of the droplet, creating a constant supply of vapor that keeps it floating. Now you might wonder, at what temperature does this effect occur? This is called the Leidenfrost temperature, and it depends on the liquid and surface properties. The Leidenfrost temperature equals the boiling point plus a superheat amount. For water on a typical metal surface, this is around 200 degrees Celsius. For water, the Leidenfrost point is typically between 200 and 300 degrees Celsius, well above water's normal boiling point of 100 degrees. Below this temperature, water droplets just boil away rapidly in violent contact boiling. Above it, they float peacefully and last much longer. Let's dive deeper into the physics. How exactly does this vapor layer support the weight of the droplet? We can analyze this with a force balance. The droplet's weight pulls it down due to gravity, but the vapor layer creates an upward pressure force. At equilibrium, these forces balance perfectly. The pressure in the vapor layer times the droplet's contact area equals the mass times gravitational acceleration. This is our basic force balance equation. The vapor pressure must be just high enough to support the droplet. Too little pressure and the droplet collapses onto the surface. Too much and it would be pushed higher. The thickness of this vapor layer is crucial. It's determined by a balance between evaporation rate and the flow of vapor escaping from underneath the droplet. The vapor layer thickness h is approximately the square root of viscosity times mass evaporation rate, divided by vapor density times gravity times droplet radius. This typically gives us about 100 micrometers. For water droplets of millimeter size, this thickness is typically between 50 and 200 micrometers. That's about the thickness of a human hair. Interestingly, smaller droplets tend to have thinner vapor layers. This is because they have less mass to support relative to their surface area. Now here's where it gets really interesting. What if the surface isn't uniformly hot? What if there's a temperature gradient? This is where the magic of self-propelled droplets emerges. When you create a temperature gradient on the surface, something remarkable happens. The droplet spontaneously moves from the cooler region toward the hotter region. It races uphill on the temperature gradient. You might ask, why does the droplet move toward the hotter regions? This seems counterintuitive. The answer lies in the asymmetry of the vapor layer. On the hotter side of the droplet, evaporation is faster, creating a thicker vapor layer. On the cooler side, there's less evaporation and a thinner vapor layer. This creates an asymmetry. The droplet tilts slightly, with the hotter side lifted higher. This tilt causes a pressure imbalance in the vapor flow, which pushes the droplet toward the hotter region. Let me explain the propulsion mechanism in more detail. This is based on viscous stress in the vapor layer and the rocket effect from asymmetric evaporation. The propulsion force is proportional to viscosity times area divided by layer thickness times the gradient of the layer thickness. The steeper the thickness gradient, the stronger the force. As vapor flows out from under the droplet, it flows faster on the side with the thinner gap. This creates a viscous stress that pushes the droplet toward the hotter side. Additionally, faster evaporation on the hot side creates a rocket-like thrust effect. The vapor jets out more forcefully on that side, pushing the droplet in the opposite direction, which is toward the hotter region. Let's put some numbers to this phenomenon. How fast can these droplets move? What forces are involved? Let's calculate some typical values. Consider a water droplet with a radius of 2 millimeters on the surface at 250 degrees Celsius. Let's estimate the key parameters. The mass is 4/3 pi r cubed times density. For a 2 millimeter radius water droplet, this gives us about 34 micrograms, or 3.4 times 10 to the minus 5 kilograms. The evaporation rate depends on thermal conductivity, temperature difference, area, and latent heat. For a droplet, this is roughly 10 to the minus 7 kilograms per second. With a temperature gradient of about 10 degrees per centimeter, these droplets can reach velocities of 1 to 10 centimeters per second. That's quite fast for such a tiny object. The Reynolds number is density times velocity times length divided by viscosity. For the vapor flow, this is around 0.01, indicating laminar flow in the vapor layer. The propulsion forces are incredibly small, on the order of micronewtons, yet they're enough to overcome the tiny drag forces and propel these miniature hovercrafts. Scientists have created specially designed surfaces with asymmetric textures that enhance this self-propulsion. These are called ratcheted surfaces or sawtooth textures. These surfaces have tiny sawtooth-shaped ridges. The asymmetry creates a preferred direction for droplet motion. The droplets consistently move in one direction, like they're on a microscopic racetrack. The key is that the asymmetry breaks the left-right symmetry. Without it, droplets might move randomly. With it, they have a clear preferred direction. This allows scientists to sort droplets by size, direct them along specific paths, and even create droplet-based logic gates. It's like nanoscale traffic control. How long do these droplets survive? The lifetime depends on the evaporation rate and the initial droplet size. The lifetime is simply the initial mass divided by the evaporation rate. For our 2 millimeter droplet evaporating at 10 to the minus 7 kilograms per second, we can calculate this. This gives us about 340 seconds, or nearly 6 minutes. That's remarkably long compared to the fraction of a second a droplet would last in direct contact with a 250-degree surface. Larger droplets last proportionally longer because volume scales as radius cubed, while evaporation rate scales roughly as radius squared. Double the radius, more than double the lifetime. Let's address a fascinating question more deeply. Why do these droplets seem to defy intuition by racing toward hotter regions, which we might think of as going uphill in temperature? Think of it this way. Normally, objects seek lower energy states, like a ball rolling downhill. But Leidenfrost droplets are driven by active processes, not passive potential energy. The continuous evaporation and vapor generation creates what physicists call an active, non-equilibrium system. Energy is constantly being pumped in from the hot surface. The droplet is like a tiny engine, converting thermal energy into kinetic energy. It's not rolling uphill by itself, it's being powered by the temperature difference. There's a key equation that describes the force driving these droplets. It combines thermal effects, vapor dynamics, and surface geometry. The force is proportional to alpha, a geometric factor, times the temperature gradient divided by absolute temperature, times thermal conductivity, times temperature difference, times area, divided by latent heat. The coefficient alpha depends on the droplet shape and the surface texture. For ratcheted surfaces, alpha can be significantly larger than for smooth surfaces. The key takeaway is that steeper temperature gradients create stronger propulsion forces. This is why carefully designed thermal patterns can control droplet motion precisely. Now let's discuss why this phenomenon is not just fascinating physics, but also has practical applications. What can we do with self-propelled droplets? First, this enables microfluidics without pumps or channels. You can move tiny amounts of liquid around just by controlling surface temperature patterns. No mechanical parts needed. Second, self-cleaning surfaces. Droplets can be made to race off a surface, carrying dirt and contaminants with them. This is useful for solar panels, windows, and industrial equipment. Third, thermal diodes. Just like electrical diodes allow current in only one direction, these surfaces can allow droplet motion in only one direction, creating fluid rectifiers. Imagine a chip covered with thousands of tiny droplets, all moving in coordinated patterns, sorting themselves, mixing, reacting. This is the future of lab-on-a-chip technology. There's even potential for energy harvesting. If you can convert thermal gradients into mechanical motion of droplets, you might be able to extract useful work from waste heat. How does Leidenfrost levitation compare to other methods of making things float? Let's put this in context. Magnetic levitation requires powerful magnets and active control systems. It's complex and energy-intensive, though it can support much heavier objects. Acoustic levitation uses sound waves to create pressure nodes that trap objects. It's impressive, but requires precise acoustic transducers and works only in specific geometries. Leidenfrost Levitation is beautiful in its simplicity. It's completely self-sustaining, requiring only a heat source. No external fields, no active control, just thermodynamics at work. Let's explore some advanced aspects. Leidenfrost droplets aren't perfectly stable. They can oscillate, break apart, or exhibit complex dynamics. Droplets can oscillate in shape, pulsating like they're breathing. These are called breathing modes, with frequencies that depend on surface tension and droplet size. The oscillation frequency for mode n is the square root of n times n minus 1 times n plus 2 times surface tension, divided by 4 pi times density times radius cubed. For our 2 mm water droplet, the fundamental oscillation frequency is around 50 Hz. You could actually hear it if you could amplify the vibrations. Under certain conditions, Leidenfrost droplets can develop beautiful star-shaped patterns. This happens when rotation and oscillation couple together. The droplet develops distinct points, typically 4, 5, or 6 points depending on the conditions. It looks like a living, pulsating star on the hot surface. This occurs when centrifugal forces from rotation balance with surface tension trying to keep the droplet spherical. It's a delicate balance that creates these geometric patterns. Here's a mind-bending connection. The way these droplets move on vibrating surfaces is mathematically similar to quantum mechanics. Some researchers are using this for quantum analogy experiments. When droplets bounce on a vibrating bath, they create waves that then influence their own motion. This is remarkably similar to how quantum particles are guided by their wave function. This field is called hydrodynamic quantum analogs. While not actually quantum, it lets us visualize and experiment with quantum-like behaviors at the macroscopic scale. Of course, Leidenfrost technology isn't perfect. There are challenges and limitations we need to understand. First, it requires high temperatures, typically 200 to 400 degrees Celsius. This limits the types of liquids and materials you can use. Second, droplets inevitably evaporate. Even with the Leidenfrost effect, you only get minutes of lifetime for millimeter-sized droplets. Third, without carefully designed surface textures, droplet motion can be unpredictable and hard to control. You need engineered surfaces for reliable applications. Finally, surface contamination can disrupt the vapor layer. Dust, oxidation, or residues can create nucleation sites where droplets stick instead of levitating. Let me share some exciting recent developments in Leidenfrost research that push the boundaries even further. Researchers have studied liquid nitrogen droplets on warm surfaces. Here the temperature gradient is reversed, but you still get levitation and self-propulsion. Experiments on the International Space Station have explored how Leidenfrost droplets behave in microgravity. Without gravity's pull, the dynamics change dramatically. Some researchers are using the Leidenfrost effect for rapid freezing of biological samples. The vapor layer provides thermal insulation during critical cooling steps. If you wanted to demonstrate this effect yourself, here are the practical parameters you'd need to know. Use a smooth metal plate made of aluminum or copper. Good thermal conductivity helps maintain uniform temperature. Heat the surface to 250 to 300 degrees Celsius using a standard laboratory hot plate. Use a surface thermometer to verify temperature. Create droplets 2 to 5 millimeters in diameter using an eyedropper. Room temperature water works fine. When you drop water onto the surface, if it's hot enough, you'll see the droplets skitter around like tiny hovercrafts. If the surface is tilted or has a temperature gradient, they'll race in specific directions. Safety first. Always use heat-resistant gloves and eye protection. Hot surfaces and droplets can cause serious burns, and the droplets can bounce unpredictably. Let's analyze the energy budget of a Leidenfrost droplet. Where does energy come from, and where does it go? Power input equals thermal conductivity times temperature difference times area, divided by vapor layer thickness. This is the heat flowing from the surface through the vapor to the droplet. Power consumed by evaporation equals mass evaporation rate times latent heat of vaporization. This is where most of the energy goes. A tiny fraction goes into kinetic energy, 1/2 m versus squared, divided by the acceleration time. For a droplet moving at 5 centimeters per second, this is minuscule compared to evaporation. The energy efficiency for propulsion is less than 0.01%. Almost all the thermal energy goes into evaporation. Yet that tiny fraction is enough to power the droplet's motion. Let me summarize the key concepts we've covered about Leidenfrost Micro Hovercrafts. Leidenfrost droplets levitate on self-generated vapor layers when surfaces exceed a critical temperature well above boiling point. Temperature gradients create asymmetric vapor layer thickness, leading to net propulsion forces that drive droplets toward hotter regions. This enables self-propelled microfluidic systems that require no pumps, valves, or external power except heat. Specially designed ratcheted surfaces with asymmetric textures enhance directional control and enable droplet sorting and manipulation. Applications span from self-cleaning surfaces to advanced lab-on-chip devices, and potentially thermal energy harvesting. Looking ahead, where is Leidenfrost technology heading? What innovations might we see in the coming years? One exciting direction is integration with microelectronics. Imagine surfaces with embedded heaters that can create programmable thermal patterns, directing droplets anywhere you want. Another direction is combining Leidenfrost propulsion with other mechanisms, like magnetic fields or light-induced forces for even more precise control. Researchers are working on scaling down to sub-millimeter droplets. At smaller scales, new physics emerges and applications in drug delivery become possible. Imagine a chip covered with an array of tiny heaters, each individually controlled. You could create complex thermal landscapes that guide droplets through intricate paths, mixing and sorting them like cars on a highway system. Leidenfrost Micro Hovercrafts represent a beautiful intersection of thermodynamics, fluid mechanics, and surface science. They show us that even phenomena we've known about for centuries can still surprise us with new applications. The key lesson is that simple physics, just heat and evaporation, can lead to complex and useful behaviors when properly harnessed. Nature has been using these principles for millions of years. Now we're learning to engineer surfaces and control conditions to make this effect work for us. And finally, the smallest scales often reveal the biggest surprises. Micro hovercrafts racing uphill on temperature gradients remind us that there's always more to discover in physics.